Let's do another problem. We'll start by reading the problem. That'll hopefully give you some time to transcribe it in case you need to write it down as part of your notes. An open top bin is made from a 15 centimeter by 12 centimeter piece of plastic. By removing a square from each corner of the plastic and folding up the flaps on each side. What size square should be cut out of each corner to get a bin with the maximum volume? I'm going to start by highlighting and trying to identify a constraint and the objective function. I always call my objective function omega, and in this case, omega is going to be volume. And maybe you find the highlighter method useful as well. I'm going to highlight in blue my constraint. And my constraint is going to be the size of the piece of plastic I'm going to cut from. Because if I have unlimited plastic, I can make a open top bin of arbitrarily large volume. So we're constrained by the size of the piece of plastic that we're cutting from. Let's draw a picture. Let's first draw a 15 centimeter by 12 centimeter piece of plastic. And let's draw a little square in each corner of the plastic, right? Because we're going to remove a square from each corner of the plastic. So we're going to fold on each of these scoring lines. And when I fold up, I'm going to get a little rectangularoid, a little cuboid. Do you see it in your mind? I hope so. If not, I want to help you see it. The dimensions that I'm going to work with are going to be those three. The product of those three highlighted dimensions gives me the volume of my object when I fold it up. We should name them. I would very much like to name the horizontal dimension x, this other one here, y, and then the one that will be vertical when I put it together is z, because that'll be like the depth of the tray that I'm making. So I have z's everywhere in these corners. Then x is only the distance on the inside of the cutouts. So z determines x. So the volume is x times y times z. It's three variables, right? Writing down the volume x times y times z is that part was pretty easy, but now we've got to get to a single variable. We need to turn into a single variable. So we need to eliminate two variables. I don't think I can eliminate z because z is the control variable. You know, like z is what I'm setting. We can't eliminate z. Probably could eliminate z, but like it'd be a lot of work, and I don't think that we should do that. I think we should eliminate x and y. So we want to find a relationship between y and z and between x and z. Take a second and think. Let's focus on the relationship between x and z on this side length right here. Do you see a relationship between x and z that constrains them? Ooh, x minus 2z. Okay, so that's an expression. What about x minus 2z? What about it? We need an equal sign in there. If it's constraining, there needs to be an equals. And I love x minus 2z. What's this total length down here? The total length is 15. Ooh. Ooh, okay. So proposes that x equals 15 minus 2 times z. Because we've got a z and an x. So if I take the whole thing and I subtract those two pieces, then I should get the piece that's left over, which is x. Exactly. X equals 15 minus 2z. A way of thinking about it to get there beforehand is also that 15 equals x plus 2z. So we've got a relationship between x and z that we can use that we're going to be able to eliminate. And went to the form that we're going to use to eliminate x over here. So we're going to use x equals 15 minus 2 times z. And now that we've done that for x, I'll bet the one for y is different. Would anyone like to venture the expression that we can use to eliminate y? Suggested that we'll have that y, which is that distance there, is equal to the total distance 12 minus the piece that we're cutting out. I have a total of 12, and I'm cutting out those, which means the leftover is just the part that I wanted, y. Wonderful, thank you so much. Y equals 12 minus 2 times z. Okay, so we're going to put those in for both of those two variables there, and we'll rewrite omega equals x times y times z. And now we've got a single variable optimization function. Let's go ahead and rewrite it by distributing things through, and then I'd like to sketch it to get an idea for where my critical points should be before I compute them. And I think that's a critical step in doing these problems correctly, is to use those graphs to help you know when you're making algebraic errors. Because it's easy to make algebraic errors. So that's going to be equal to 15 times 12. That's first. Outside is going to be minus 30z. Inside, minus 24z plus 4z. All of that's in parentheses times z. Oops, squared. So omega equals 15 times 12 times z minus 54z plus 4z cubed. And I'd like to just pop over here and do a quick little sketch of it. I know that it is, check it out, this is that kind of cube because it's positive, because the sign of the leading term is positive. So I know it's a cube that looks like that. And omega has roots at z equals 0, z equals 6, and z equals 7.5. See how each one of the terms in the product gives you one of the roots? I've got roots at 0, 6, and 7.5. Okay, so I'm going to put down 0, 6, and 7.5. And I know that I have a cube that goes like this. So there's my sketchy sketch. Super shitty sketch. And check it out, I should have critical points there. I should have 2 crit points, 1 in the interval from 0 to 6, and 1 in the interval from 6 to 7.5. So as I go through and find my critical points, I better find 2, one between 0 and 6, and one between 6 and 7.5. See, I love using graphs because I already know something about the answers I'm going to get, which is going to be a great way for me to check my work because it's easy to make algebraic mistakes, yeah? Like, you make mistakes, I make mistakes. I'm not perfect. Let's find the critical points. There are no critical points where the derivative is undefined. The derivative is defined everywhere. Okay, so all critical points are the form omega prime equals 0. And the reason that I wanted to distribute out omega is because I don't want to deal with a triple product in that. Like, that just sounds terrible. I think this times 12 here is disturbing me. So I'm going to write that a bit nicer. There we go. Okay, so I'm going to take the derivative, omega prime, and it's going to be 15 times 12, coming from that term, minus 108 times z plus 12z squared. When I do not readily know how to factor that, maybe one of you does, I'm going to choose to use a quadratic formula to find the 2 values of z once I set it equal to 0. So I'm going to use the quadratic formula. The quadratic formula is going to say that z equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And now let's just run that through a calculator, shall we? So let's open a parentheses, and here's going to be our numerator, 108, plus, we'll do the first one first, plus the square root of 108 squared, minus 4 times 15 times 12 times 12, minus 4ac. Right, get out of there, divided by, open a paren, 2 times 15 times 12. I got z equals 0.45275, and I can use the second entry to recall my previous entry because I want to compute the other root. So it's, remember there's plus or minus for the two roots in the quadratic formula. So I'm just going to mouse left here, and I'm going to delete and replace that with a minus sign. And I enter, and I get z equals 0.147247. I don't know. I think I made a mistake because look at these two values and compare with what we found by doing our graph. These are wrong because both are in the interval from 0 to 6 and none are in the interval from 6 to 7.5. I know I made a mistake. Now I have to go back and hunt for what my mistake was. I'm doing this deliberately because I want you to feel okay with making mistakes. I want you to know that making mistakes is inevitable and that there are ways to help us catch those mistakes. And that's precisely why I do this, precisely why I rely on pictures and graphs to help me out with this. So I know that both of these are wrong. So let's go back and hunt in our work and see what we did between here and here that caused the problem. Oh, minus 108? Okay, so here there should be a minus sign. Okay, so let's make that modification. But I don't think that changes anything because minus 108 squared is the same thing as 108 squared. So like, while that is true, and that maybe that should have been minus 108, it doesn't actually change the value of either of these two values here. I don't think it's this one because this is negative. Remember, that's negative b in the bottom 2a. So maybe we should investigate in this and label our values for our coefficients. I know the one in the middle is b. Which one is a? Oh, a. Oh, but look, I have 2 times. Oh, I have 2c in the bottom here, don't I? I have 2c. So that 15 was incorrect because a is 12. Part of the mistake that I made here was that I wrote my function where the leading term wasn't in front, right? So like I just took my coefficients front to back, but they weren't in the right order for me to do that. I needed z squared to be the first one and then work my way down in terms of powers of z from there on out. So I know the denominator, I shouldn't have a 15 here. Are these other terms right? My 108's right. What about this one? Is this minus 4ac? Is that part right? That looks good to me. Got my 4, and I've got, whereas before I thought I had, so I have CA, but fortunately 4CA is 4AC because multiplication over the reals commutes. So that part's good to go. Okay, so I think all I need to do in order to get my correct answers, and I'm going to use my second entry button to recall the last thing I did. And I'm going to go over a few characters and I'm going to delete that so that I have 12. Yeah, that looks right. Okay, go enter. Ooh, okay. Yeah, that looks good. All right. So now we know that z equals 2.2087 and some stuff. And I can get the other one by going second entry, and I can change that minus to a plus. Delete, plus. I go enter, and I go z equals 6.79128 and stuff. So we caught an error, and now let's do the qualitative check. Let's use the graph of the objective function, and things look good now. I have one value, 2.21, that lives inside of the interval from 0 to 6, and I have another value, 6.79, that's going to live between 6 and 7.5. Matches qualitatively, and so now I believe that I have the correct answer. I'll go ahead and label these two values, that I have 2.21 and 6.79 as my two critical points on my objective function. I can look at the graph, and I know that the one I'm interested in is the one where the volume is positive, because for this one here, the volume is negative. See how the volume is negative? It's below the x-axis, because that's a plot of the volume function. And while it does look like the volume goes off to infinity over here, those are unrealistic values of side lengths to cut out because I don't have that much plastic. So I can discard that one because the volume is negative, and that's the one that I want. That's my maximum value. So we found a critical point, and we found the one that I wanted. As the last step in this process, we need to interpret. Right? We have to go back and look at our problem and see what am I being asked, because sometimes they'll want, what is the maximum volume? And if that's the case, I'm not done yet. I need to go evaluate the volume function there. But I am done because this is what size square should be cut out. And we've answered the question now that that's 2.21 by 2.21 is how big I should cut out. Rounded to 2 decimal places. Round as necessary in the problem that you're doing. That was a little bit more complicated because it involved substituting away 2 things, not just one, but 2.